I start the recording and the presentation as well. Okay, let's start with the this will be the talk of today, but let's jump I don't know. The problem is that I'm not very familiar with Teams. Perhaps the person is online, perhaps not. If he hears me, then perhaps can send me something. Okay, so what happened? I created the module and Teams groups. It was very interesting. I have to ask in the Neptune. And then they generate. First they generated all module groups, that's fine. And then one Teams group for everyone. Actually, the practice with the members of this practice that is on Friday. And yesterday they made all of this stuff. So I upload the notes. Thank you for sending. Some of you, Mr. Khan, send me. You find the second notes. There is a lecture note in Hungarian and also some other stuff. I shared everything with the Hungarian and students and you. Yes, I modified these slides because its English was not the perfect, and also I added some picture because I had no time to do it, but now, yeah, we do something else. So last time, yes, someone is online? Yeah, perhaps, I don't know. I want to share my screen. That's the problem, perhaps, because I forget, no, okay. The screen. Whose screen? And the first screen. Great. Okay. In theory, it is visible. Okay, so last time I gave a definition of what is vector, how to multiply it with a scalar, addition and subtract of vectors. And and I also gave some features. When you will do any operation, any deduction, you have to use these features. So now it's not like a number. So today we will have other business to do. It's here. Okay. Yeah. Great. We have vectors. And there is some some. Last time I defined what is the unit vector. The unit vector is a vector which could have any direction, doesn't matter, but the length of the vector is 1. We defined the length of the vector. If you have components, then you just add together the square of the components and do a square root. That's the unit vector. If you are in 2D, then you can appoint two vectors, preferably perpendicular to each other, and these will be the unit vectors of the coordinate system. If you are in 3D, you can do it in with the three vectors. And you can decompose the vectors in two dimension. You can decompose all vectors to two vectors as and the original vector will be the sum of this. And in three dimension you can do it with three different vectors. And these vectors could be a number multiplied with unit vector. So you have a coordinate system. And okay, this class is not a very, very strict mathematical class. It should be, but a real mathematician wouldn't be very, very happy with this what we do. So I have a definition, and I have a statement that all v vector in three dimension could be decomposed in this way. The components multiplied by the unit vector. How can you prove this? You have this vector. This vector have the okay. So you have this vector. This vector has the components, and you can decompose. You can get this vector as the sum of three different vectors. This three different vector is it's better. Yeah, you should have told me. So if you have in two dimension, and that's not visible. So you have an A vector. It's a general rule, but I said, and this direction, I don't know. First, very generally, no, this way. You can select other vectors. It do not need to be perpendicular, but in this way they are perpendicular. Their length is 1, and that's a number. And then you can decompose this vector, two vectors, and something v1 times a1, and this one is v2 times e2. So I don't mention any coordinate system, but actually you do this. So you have a vector, and you can decompose it for two vectors. And if I appoint these vectors, this is a unit vector, then these vectors can write as multiplication of a number and this unit vector. And what we do here So I have in 3 dimension one vector. I should so we have 3D, and I have a vector. I can write this vector in this way, and this is my vector. This is this V. So I project it here. Sorry, until here. So that's the V2 component. Then, it's difficult. More difficult. Just a moment. So this is the V3 component, we could be sure. This is perpendicular, this is the V1 component, and also perpendicular, this one. So these are the components. And if you remove the coordinate system in your mind, that's one vector, that's an other vector, and this is a third vector. So these are quantities. This is V times E3. This is V2 times E2. And this is V1 times E1. So, what I write here, I have a V1 that's in components this one. I could say it's nothing more than V1, no, here, V1 plus V2 plus V3, and these vectors are nothing more than V1 plus sorry. Yes, and these are V1 It's perfect. So I finished and I covered it, and half of the class cannot see. So this is what we wanted to prove. Okay. So we have what we have. So I prove this. That's simple, very simple. Okay, let's. Next step. If yes. If you have a vector, you can do the normalization. So if the vector has a direction, it's not a null vector. That's the only vector which has no direction. Then you can calculate the magnitude of the vector, and you can divide the components by the magnitude. And then you will get a unit vector whose direction is similar to the original vector. I do this quite frequently in my job in physics. Okay, great. No, not yet. It's too far. Okay, so this is you have a. Could you write this down?
Yeah.
Yes? Okay. Fortunately, it's still quite simple, but don't worry. This will not last long. Okay. You have a v vector. This is the length of the vector. So if you have this, you divide the length of the vector, you will have a vector which has a unit length and the direction is the same. Or you have this vector. You can calculate the length of this vector. That is it's not a swearing. So this unit vector length will be okay, is it understandable? You have a vector, so this is with the vector. This is with components, and you calculate the length of the vector and divide the components, all components, with this length. So I could actually write here. It's and so on. So I don't want to write all of it. Tomorrow I will give numbers and we will calculate some things. This is what we do quite frequently. Okay, next one.
Excuse me?
Yes?
Can you please explain the last one, 1 divided
This
by
one?
square? Yeah.
This. What explain? I have to take the sponge. Where is the sponge? Here. And write it again because it's too small. That's why you cannot understand. Please tell me when you cannot see. So you have a vector. You calculated the length of the vector. That's the length of the vector. So instead of E, I would use N like normal vector. Just in the note, they use E everywhere. So the normal vector of this V vector will be what I got? It's V, not X. Sorry. Okay, so I wrote using larger, in larger. What I had done here, I have a vector, it has components. I calculated the length of the vector, that's the square root and under the square of the components. So V1 and the V2, V3. And so do the multiplication for all components. And the result will be just, I can move this before the components, and I will got. This is the normal vector, which has the direction of the V vector. That's okay?
Yes.
Okay, that's still quite simple. Okay. And we have an, oh, we, 0.1. I have another point here. It's 0.2. I need to go to the gym to prepare for these classes. We have points, that's fine. We have a coordinate system. We can give, oh, sorry. Okay, in this way you cannot see the great. We have 2 points. We have the coordinates in a coordinate system. It's a Cartesian system. We can give the position with a vector. Okay. And that's it. So the position. Okay, what can I say? So it could be R. No, P. No, R is better. P. R. R1. That's not visible. Excellent. No. Okay, this is R1. R2. And I just say the coordinates of this R1 is the same like the point. And this so if I want to determine the point, the B section point here, then I have to say it's what is the sign? Let's call this M. It's this. Why? It's quite simple, there's no deduction, but so if you so if you check, this is this point, you can go here It's halfway not only here, but also here. And this is the R1 plus R2. So if I want to come the halfway, then it's and I did the same with the coordinates. Okay. There are more important things to do. You can, I will show you generally this when we have a practice. If we want to determine the distance between 2 points, actually from the secondary school, at least my secondary school, it's quite simple. You have the coordinates Px, y, z, 1 with the index, and you just apply generally the Pythagoras theory, and you got this. Or you can do something else. You can say that you have an E vector and a B vector, and their difference, I mean the subtraction vectors, length is the distance. Doesn't matter. Actually, it matters. Let's go back here, and I have this wonderful image. We don't need this. They don't need this. I have 2 points, and the distance of 2 points, the points are equivalent with R1 and R2 vector. The end of the vector has the same components, same coordinates like the points. So the distance between the points is this one. This D is, just a moment, I said R2 minus R1, so I need a vector to add to the R2 to get this. This is the D vector, and this is the D vector, just remember. I said, oh, that's dangerous. And this is nothing more than so this is this vector. The length of this vector is the length of this, and that's this is it. Only difference is, if you can see, the indexes are the opposite, but it does not matter because it is on it's square, so it means it doesn't matter. So the sign is of the distance disappearing, or with other words, the distance between point 1 and 2 is the same like point 2 and 1. So it's quite trivial. It is. Hop, 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 hop. Okay. This is very familiar. So this is the equation of a sphere with a radius, and the center is this x0, y0, z0. So this is the equation in 3D for a square. It could be in 2D, 4D, whatever, but this is in 3D. What we have? We have an R0 vector. The coordinates of x0, y0, and z0. I want to describe something object, so I have a variable vector. That's the r with coordinates of x, y, z. And we have a distance, a radius, that's a. No, it's not a vector. So if this, I should call my daughters because they can draw much nicer than me. So this is the center of this point, and we have this variable. So this, sorry, it's very ugly, but I will upload. I will give you better plots. I have a point, a vector on the surface. I have a center point, and the distance is a. So it means that I'm looking for this and that one are the same. Just in the first place, I don't use these signs. And which is easier? This is written in this form, but if I change this 3 for 2, I got the circle, and if I change it for 4, I got the hypercircle, hypersphere.
What does that mean?
That's interesting. That's not part of the matter. I will not ask in the exam. 30 years ago, the Scientific American, the translation to Hungary, I was in the secondary school, and there was some funny computational task. One was to plot the three-dimensional profession of the hypercube and the hypersphere. What does it mean? Do you remember the title of that novel? Okay, this is yes. I tried to find it and then translation. It's not just a moment. Yeah, this is it. But this is in Hungarian. For the Hungarians, you can. Oh no. Okay, so I'm looking for the English. That's the problem when you read this in Hungarian. Edwin Abbott. W, my W. Yes. Yeah, okay. The translation is trivial. Flatland. Yes, this is it. It's quite old. Flatland. You can take it and read it. Okay, what does it mean? There are dimensions. And here, in this class, we are dealing with 2 dimension and 3 dimension. But there are more dimensions. 0 dimension is a point. 1 dimension is a line. 2 dimension is a plane. 3 dimension, space. And here, I draw 3 perpendicular axes here. X, Y. This is a projection from 3D to 2D, so it should be perpendicular, but it isn't. Y, Z, and also this is perpendicular, and also the X and the Z is also perpendicular. But you, not me, could draw a 4th axis that is perpendicular to this 3. What does it mean? That's a 4th dimension. For example, in a special and general relativity theory, you can use it. What is a sphere, a circle, in a different spaces? 0 dimension, it's a point. A segment is in 1 dimension. 2 dimension, it's a circle. 3 dimension is a sphere. And in 4 dimension, it's so-called hypersphere. Also, if you check the cubes, 0 dimension cube is a point. 1 dimension is a segment. 2 dimension is a square. In 3 dimension, it's a cube. And in 4 dimension is more difficult, but this is what I can do for you. My limited abilities. This is just a cube right now. And within this cube, and I cannot go this here. This is it. Sorry, it's not perfect. BMW, Budapesti Nagyvásár, for Hungarian students. The logo was that one. This is in 4 dimension, but you cannot see the fourth dimension. So this is a projection from 4 dimension to 3 dimension. So this writing and what I wrote is a general stuff. In particle physics, you could have 100 dimension ratio, 100 dimension or more. I think it's interesting. That's why I mentioned it. It's not part of not part of the lecture. Just what is it? No. Okay. So we have spheres, we have distances. Do we have time? Oh, not so much because I was late. Oh, good. Okay. There is a very, very important definition. I have multiplied vector with a scalar. You can multiply 2 vectors. There are 2 different ways to multiply them. The first one is the scalar. This is the scalar. There is a typo here. Multiplication of 2 vectors. A and B vectors scalar multiplication is the length of the vector multiplied the angle of the cosinus of the angle of the vectors. So we have 2 vectors. And we got one, one number. This is important. But what can I do? I have an A vector, I have the B vector, and I never use this. I hate this. Just so I use dot. This is a dot. If I don't write, then it's a scalar. And this is, by definition, is the length of the vector, this one, so this, the length of the other vector, and this, do you like gamma, theta, theta, theta is nice. This is a definition. You have 2 vectors in representation with components, you got one number. This is one definition, and this is a very nice definition because of this. It's a tool for me. Okay, let's remark that if you have the same vector, yes, it's okay. So if you multiply a vector with itself, then you got the length, the square of the length of the vector. Okay, there are features of this scalar multiplication. It's like programming. If you do anything with vectors, the operations are all of here. What are these? Since these are not numbers, you cannot do anything. You can do only which is written here. First, if you multiply vector B with vector A, then it's same like multiply vector A by vector B. How can I say it? Multiply vector B with A is multiply vector A with B. So it's commutative. You can change it. There was another word here, but I think it's not very good. If you have two vectors, I mean the total, the sum of two vectors, and you do the scalaric multiplication, then you can do this. Actually, this is not not the good term. I will change this, but we have 10 minutes. I should prove this, but so if you have, so the second equation is also so it's true. If you multiply a vector with a lambda number and then do the scalaric multiplication, then you can remove from the scalaric multiplication this lambda number. And if you calculate, you multiply a vector with itself, then it is 0 only if the A vector is the null vector. Otherwise, it's larger than that one. It's trivial because this is the absolute value of the vector. Okay. Yes. This is an exception because I could write this easily. This is a statement. If you have an A and B vector and you have the components A1, 2, 3, B1, 2, 3, then the thesis says you can calculate the scalaric multiplication with multiplying the components itself and add. So this formula that you should memorize. In the next slides, I will show you tricks that we use this. To deduct and prove this is quite simple. Remember the definition of the scalaric multiplication, vector multiplication. If so, the angle of the vectors are in the formula, and you take the cosine of this. 0 for 0 angle, the cosine is 1. For if the vectors are perpendicular, then the then this cosine is 0. So normally this stuff is a lemma, but here just go through. You have two vector you have two vectors A and B. You can write the A in this form in components. There is a typo. The A1 is just normal number, A1, 2, and these are unit vectors. These are the canonic decomposition. If you do if you do the multiplication, so you multiply with this, and this, and then this, and this. That's okay. This and this doesn't matter. I wrote it down, and these A1, 1 are the same, so the cosine will be 1. These are perpendicular. These are perpendicular. This is not. This is 0, 0, 0. So if you sit down and check this, then you can see only A1 times B1 plus A2 times B2 and E3 times B3. So the sum of these components, the multiplication of these components will remain. Is it understandable?
Yes.
Okay, great. So you have this. This is what we wanted to prove. And now I can show you the next stuff. Perhaps, no, it was the Hungarian practice group. I have two equations for the scalar. I have two equations for the scalar multiplication. One says, okay, A times B is A we know what is theta, and we also know that it's a bit painful. Doesn't matter. This is a girl. So I have this length of the A vector times length of the B vector and cosine. Then we can determine the angle of the A and B vector, actually the cosine of the angle, very simply. It's quite simple, and it also works not only 3 dimension but 2 dimension, and it's right of Wunderwaffe, Wanderweapon. So I use it quite frequently when processing data. It's okay?
Yeah.
On practice, we will calculate this. I will give numbers for vectors, and we will calculate. Perhaps we had done, I don't remember exactly. Okay, next one. It's a definition. If A and B vectors are perpendicular, but usually we say orthogonal. Why? It sounds better. No, I'm just kidding, but you will learn in algebra what is orthogonality. There is a general term. So if A and B vector are perpendicular, then their scalar multiplication is 0. It's trivial because you have A and B. The angle between A and B is 90, so the cosinus is 0. So then it's 0. So if you see that it's also a tool. I wrote vectors, but imagine you have components, and you use this form, this So I use this form, and the result is 0, then the two vectors are orthogonal. Very often you have two vectors, and these are somewhere, and you cannot how can I say, cannot see that they are perpendicular or not. This is a tool for it. I will show you. Okay, and there is something that's more difficult, and I don't know what we will do with it right now. And this is the last one. I have an A vector, and then I have a B vector, then I have this perpendicular line, and it's grammatically difficult. The perpendicular projection of A vector to B vector is this one, and this is the sign. So this this is the projection. For the projection, not with vectors, with other, we will deal a lot with operators, matrices. This is just, I think, a preparation or something like this. Okay, and you can calculate this using this formula, the scalaric vector of A and B, multiply by B, and calculate with B. On practice, we will do this. Last comment, very last, and I will dismiss you. If the B unit has a unit length, then the form in this form. Okay. So that was it. See you tomorrow, and I will upload this, and I will add some explanation, some plot. Okay.
Thank you.
You're welcome. Okay. Excuse me?
Will you upload this today? Will you upload this today?
Usually I do it at the weekend. Okay, what else? Everyone could reach the module and the Teams group now. It's okay. You can see what I upload. Okay, great. If not, send me. Yes. Yes. Okay. It's okay. Have you studied this? So why don't you go to the Department of Studies and ask them for credit translation?
But the problem is this only part. This vector was just a part of another subject, so I couldn't transfer.
Have you asked?
Yeah.
Wait.
I applied for the head of transfer.
And what?
They still haven't got it back.
Okay, doesn't matter. This will come to me. So come tomorrow. You can this. Everything there. It's okay. And if it's accepted, then you don't need to start. I will look what you studied and I will accept you.
The thing is, I didn't take the algebra course. I just took vectors and type. So I know everything about it.
What I learned doesn't matter. Yes? You don't like about it?
No, I don't want to transfer the credit for the whole.
But you are familiar with this. Actually, this is still a secondary school.
Yeah.
Still. So
That's
it's a
secondary school and university. You took it as well.
Okay.
Okay, just
Okay. You're welcome. Okay. Bye bye. Oh. Yes?
Sorry, Professor, I wanted to ask about the exam test, I guess. How will that be? I know it's still early to...
I stop the translation, just no, the record, okay? Because someone is in line. So I stop the record here.